team of astronomers using a network of radio dishes to peer to the edge of a massive black hole at the heart of a galaxy that is 50 million light years away. For the first time, they have measured the invisible boundary around the black hole. It's called an event horizon, where nothing, not even light, can escape its strong gravitational pull. So what secrets did the astronomers uncover at the black hole's edge? Shep Doeleman is the lead author of the study, which was published last week in the journal Science. He's assistant director at the MIT Haystack Observatory in Westford, Massachusetts. Welcome to the program.
Hi, Everett. Good to be here.
Thank you. What exactly is an event horizon?
Well, let's back up a second and ask what a black hole is.
Okay.
It's a great question. That's where matter has collapsed in on itself gravitationally so that it becomes a singularity or a point of basically infinite density. And when that happens, even light cannot escape the intense gravitational pull. Mm-hmm. And around that singularity is something we call the event horizon. Right, that's the exact point in space where light cannot escape. Mm-hmm. Right. But we see black holes, which is kind of a paradox, because you would think, well, if light can't escape, then how do we see it? And we see it because black holes are really messy eaters. They're trying to attract all the gas and dust around them into a very, very small volume, and the compression heats up that gas to billions of degrees, and that's really what we wind up seeing. It's a bit like trying to drag an elephant through a keyhole, right? A lot of stuff is trying to get into a small spot, so you wind up seeing the mess.
And so you've measured that boundary around the black hole.
Well, we didn't exactly measure that. We measured. We looked at a very interesting source called M87, which is a giant elliptical galaxy, mm-hmm. and at the heart of it is over a 6 billion solar mass black hole.
6 billion times the size of our sun.
The mass of our sun. Right. So imagine 6 billion suns inside something the size of our solar system. It's just kind of phenomenal to think about.
Mind-boggling, yeah.
And the gravitational pull is so intense, it's drawing all this matter to it, which is inspiraling like water down a bathtub drain. So you wind up getting a pancake of material orbiting this supermassive black hole. And what specifically we were looking for is the fact that there's a relativistic jet of high-speed particles just screaming away from this black hole and its disk. And we imaged the very base of that jet, which we think is anchored in the innermost part of that pancake of inswirling matter. So we didn't exactly measure the accretion disk, we measured this innermost orbit, which is a very interesting point in space.
Well, why do you want to know that?
Well, it's a great question. We know that about 10% of supermassive black holes in the hearts of these galaxies issue these amazing jets. And these jets really are some of the most powerful phenomena in the universe. They can go for thousands, hundreds of thousands of light years. And it's been thought that the combination of a spinning black hole and this pancake of inspiraling matter power that jet. And it does so by dragging magnetic field lines with it to the very edge of these orbits. And the magnetic field lines accelerate particles much like a bead on a wire would be flung out by, if you had a wire and you were flinging it above your head, a bead on that wire would zip off to the north and south poles, and that's what happens with these jets. But we haven't had any data on size scales close to the black hole that can constrain the theories that have really been relegated to supercomputers and simulations.
So have you narrowed down a theory?
Well, so we found something very interesting. When you get so close to a black hole, Einstein really tells you what you have to see. It's completely outside the scope of our everyday existence. So, for example, satellites, in theory, could orbit as close to the Earth as they want, but near to a black hole, all bets are off, and there's an innermost stable orbit, inside of which anything just falls in. So there's a limit to how close you can orbit to a black hole, and that's where that pancake of matter gets hottest, densest, and most threaded with magnetic fields, so that you can wind up getting one of these jets. And that size is determined by the spin of the black hole. That's the first thing. And the second thing that makes this possible is that the black hole is so massive and the gravity is so strong that light gets bent like taffy, so it magnifies the apparent size of that innermost orbit. So we think we know pretty clearly the size we should see if the black hole isn't spinning. And we saw something that was much smaller than that expected size, which is very good evidence that the black hole has to be spinning.
The spinning would make the size smaller?
Exactly. A spinning black hole frame drags or drags space-time around with it, and that allows matter to orbit closer to the black hole than if the black hole were not spinning.
See, because in our logical mind, when we see things spinning, they sort of expand out, right?
Exactly.
We think it's centrifugal force forcing it out, but you're saying because it's dragging time and space with it, it's closing smaller, getting closer to the center.
Exactly. It's an energetic argument.
It's amazing.
Well, basically, when you are orbiting a black hole without spin, the energy profile, if you will, of the orbits sets the point at which the innermost orbit can be. But when you rotate the black hole, you can drag matter around with it and allow that matter an energy orbit that can bring it very close to the event horizon itself.
And you used a whole series of ground-based radio dishes for this? You sort of created a giant dish out of many?
Yeah, so we used a very interesting technique called very long baseline interferometry, where we take radio dishes around the world and we record data at them simultaneously, pointing at this galaxy, M87, and then we bring it together to a central supercomputer that acts as the lens. So we effectively get a telescope as big as the Earth. And we absolutely need that because, we need a magnification power that's about 2,000 times better than the Hubble Space Telescope to do this work.
Wow.
So as an analogy, if we're in New York and we're looking at a mail truck in Los Angeles, the Hubble can kind of make out that there's a mail truck there, maybe. But if you want to read the letters inside that mail truck, then you need this array that we've built called the Event Horizon Telescope.
And scientists are never happy with what they have. Right?
It's really true, as in science, as in everywhere.
And you want more, don't you?
Yeah. Well, we have enough now to make this interesting size argument. We've seen the base of this relativistic jet, and we've determined that the black hole is probably spinning, and that the accretion disk is orbiting in the same sense as the black hole spin, which is a very important part of it. But we want to increase the resolution, so we want to put telescopes all around the world now. So we have plans to put one in the South Pole, in Greenland, Mexico, and Chile, and we're going to incorporate some telescopes in Europe to really make an Earth-sized virtual array. And that will give us the coverage and the resolution we need to actually start to make images and pictures of the glowing gas right around the event horizon.
If you could put one in outer space or on the backside of the moon, would that help you?
Very, very interesting point. Probably we would start over-resolving the black hole. There's a limit to the size of the structures we expect to see there, and it could be there'd be nothing left to see, because if you put a telescope on the moon, you'd have such high resolution, such high magnifying power, that there might not be anything left to see, right? You'd be looking kind of at the side of a barn with a magnifying glass. You wouldn't really see any contrast there, if that makes sense.
Mm-hmm. Let me get a quick question in here before we have to go. Let's go to Chino in Fredericksburg. Hi.
Hi, this is Chino, calling from Mary, Washington. I have a question. I understood black holes as, they're in three-dimensional space, and often they're described with this hole shape or flat shape. I assumed as a way to just get people to visualize it, like a manhole cover, things fall in. And what I'm hearing is a continuation of that explanation, but I'm having trouble reconciling that with my understanding that it's in all directions. Isn't it in all directions? There isn't like a hole in space. Everything's falling in. It's in every plane, in every direction from that you would approach it.
Right.
Am I right?
Yeah, you're exactly right. The analogy of like a rubber screen with a bowling ball in it that bends the rubber screen down, that's really for visualization. In space, you're looking at a three-dimensional object. So the event horizon is this very dangerous and spooky boundary around the black hole through which, once you go, in any dimension, you're never coming back. It's kind of a knot we can tie in the universe and never untie. So it's the only place in the universe that you can leave and never come back. But it is a three-dimensional object, and as I was saying before, the energetics around the black hole make it a point in the universe that is really beyond our everyday conception of the way things work.
What do you need to know about a black hole that you don't know already?
Well, it's a great question. Well, it turns out that if we can make images of the glowing emission around a black hole, we can begin to ask some questions that we haven't been able to ask before. One of which is Einstein right? So we have this beautiful general relativity theory from Einstein, but it hasn't been tested fully in the one place that might break down the universe, right at the edge of a black hole, because that's where gravity is a dominant force. So one of the very interesting things we're looking for is what we call the silhouette, or the shadow of a black hole, and that's when light beams from behind the black hole actually get bent around to our line of sight, creating a ring of emission with a relatively dim interior. And so we get this shadow feature, and the exact shape and size of that shadow is prescribed by Einstein. It's kind of interesting when you think about it. We make this Earth-sized virtual telescope, we observe this galaxy, and we might be able to see a shadow. And to understand that shadow, we have to go back to equations that were written 100 years ago by Einstein and Carl Schwarzschild.
Isn't that kind of the same experiment of the starlight going around the sun in the 1919 eclipse?
Precisely, and that's what really put Einstein, made him a household name.
Right.
And now we're in a stage we can say, well, and that's when Einstein said, well, Newton's wrong.
Right.
And now we're bizarrely at a point where we can ask, well, was Einstein right? And to do that, we need these very advanced techniques, this VLBI technique. But the bending of starlight, that wonderful experiment during an eclipse, showed us that Einstein was right in the low gravity regime around the sun. And the sun is just the sun. But around a black hole, the gravitational field is so much stronger that even small perturbations to Einstein's theory should show up.
Wow, that's exciting. Good luck. Good luck on that. We'll stay tuned.
Yeah, well, it's an international effort. A lot of people working on it, and we hope to have more to report soon.
Well, thank you very much, Shep.
All right, take care.
Shep Doeleman is Assistant Director at the MIT Haystack Observatory in Westford, Massachusetts.